Hello, guys. My name is Emanuele Marconato, and I'm a PhD student in the National Program for Artificial Intelligence. I'm under the University of Pisa and the University of Trento, and I'm at the PhD program for AI for Society. Um, so This is the first meeting for the SML Journal Club. So this is post-session recording, since we had some trouble the first one. But okay, so I'm going to tell some things about what we will do, and so we try to have this discussion on scientific topics, mainly on artificial intelligence, machine learning, and computer science. And this kind of discussion are open to all the interested people that want to keep in contact with us. We try to keep a blended modality so that if possible, you can follow us at a distance, and also we keep that to have some invited speaker. We are planning to have some speaker also from abroad, and we try to keep that every Friday at 4 p.m. And since this is open to all students, researchers, and professors, we also invite you to have a drink with us after the talk session. Okay, so I'm going to present today this paper, and through the presentation, I will give you some ideas about what is the motivation and what are the key challenges. This paper has been published recently, and so we'll give you mostly my take on representation learning. So I will start from a brief recap of what representation learning is treating. Then I will go distinguish between machine learning causality and discuss whether causal representation learning is a reunion. So nowadays we are facing limitation of machine learning. There are important results that regards the possibility to generalize over a huge number of data, but still we are rooted on the IID hypothesis of independent and identically distributed data, and machine learning models do not work well outside of it. Also, they are weak against noises and confounders, and those noises that can be very, very little for as humans can be truly confounders for the prediction of a machine learning model. Also, once the model is trained on a given dataset, is only tailored for that, in the sense that we cannot use that machine learning model for other domains. And also, that's why we are not gathering any knowledge beyond what is typical statistical reasoning. So we would like to go beyond that, and to be able, even in machine learning, to understand what is the relevant information, even in noisy context, and to be able to generalize outside the distribution. Also, to infer physical or causal relations among data. And this is a form of transferable knowledge to other domains. And in this talk, we are taking the point of view of representation learning. So we try to learn useful representation of data and see how, by means of that, we can go and check these all three desiderata. So representational learning started very recently. So there's been in 2013 first review of this research field, and what's really behind representational learning is addressing the learning of those factors of variation that are extracting a useful representation of our input data. So we are trying to learn a map R from the input space to representation space that is useful. And we work under the hypothesis that since typically the input distribution P of X is intractable, we can hypothesize that this originated from a simpler latent distribution P of Z, such that the input distribution we are observing is just the marginalization. And also we try to learn the decoding function, which is the probability of seeing a given input given a latent factor. And this is the objective of representation learning. So in the state of the art of this field, there are the so-called variational autoencoders, and the problem of learning latent representations is divided into pieces in the sense that we have the first one, which is an encoding that's encode from the input space to the latent space. This is done typically with a convolutional neural network for input images. And then we have the coding function from the latent space to the input feature space. But also there is some agreement in what representation are useful, and these are the so-called disentangled representation. And the main idea behind disentangled representation is that by changing only one latent factor, we are not affecting the other. This is done in a variational autoencoder by trying to pushing the encoding distribution, what is also referred as the posterior distribution, closer to a prior distribution, which is taken to be factorized. And so this promotes the learning of independent lambda dimensions. But there are limitations on that, in the sense that this works only on idealized datasets, and also having what could be a useful or suitable prior distribution is referred as the prior hold problem. And that's difficult to match, say, the posterior distribution support. So up to that, we can try to see what causality offer to as an integration for representation learning. And so to understand what is the novelty, let me take a step back and just describe what are different modelization that we have, that we can do from data or in different contexts. So the most basic one is the so-called statistical modelization. And in the statistical modelization, we are able to predict the IID setting. And also machine learning involves learning from data. But on the other hand, we do not have the possibility to predict interventions or any distribution shift. This is something that is provided in causality, and in causal graphical models or structural causal models, we have the possibility to predict interventions. So to understand what are these interventions, in the statistical modelization, we are just concerned with the input distribution. So we are learning how data are distributed in the feature space, but we're not able to predict how the distribution changes by having some intervention on the factors. And so this can look very, very different based on what kind of causal model we have. And so that's why it's referred that causal relations contain more information than the usual statistical ones. And the highest level of modelization are the so-called structural causal models. So these are direct acyclic graph that are defined on sets of observables, so sets xi, such that each observable xi is a local function of its parents and a local noise that is independent from other noises of causal variables. And in this way, we obtain the causal factorization given by this conditional structure. And so we have directly by the mathematical modelization, we have interventions, so we are able to explain them, but also we can explain counterfactors. So let's say that we want to change negative prediction for receiving a loan of an house, and we want to understand which kind of interventions we should do. So we should try to change income, job, or education, and let's see what happens. So that will be a counterfactual explanation. So also in structural causal models, we have what is called the independent causal mechanism. And this is the independence between two causal variables that do not share the parents. And in that there is no influence. So by changing one mechanism, the other ones are independent, so they are not influenced by our action. And also there is no information, in the sense that by knowing while a mechanism, we do not have any information on the others. So the idea, to bring causality into machine learning will be the first place to infer what are the causal variables from the low-level input features, and that will be, let's say, something that is inside the representation learning, but still there is the open challenge to define what aspects of data should reveal causal relations. So there has been some progress in that. They're very preliminary results. So there's a paper that tried to integrate the learning of causal representations. So starting from the hypothesis that the underlying model should be a causal one, we treat data that are causally related. So then we filter with an encoder our input information, and then we map the input sensorial data to a disentangled representation. And we know that disentangled representation is a very simple causal factorization because it has all independent variables, so there are no parents. So in practice, what happens is that the decoding function learns the factorization that is contained in the generation of data, and then conditional distribution for the output generation. And so this has been shown to be quite a difficult task, And also by learning interventions, we shall take in consideration data sets that are different from the usual IID. And so this poses another challenge for causal representation learning. Okay, so also from a more mathematical point of view, the fact that we are trying to learn causal representation from data that we are observing we're requiring in the first step to understanding what are those constraining maps that preserves important relations among data. And so, for example, take the very complicated structure of a protein. And by coarse-graining the information, we are reducing the, uh, the, the description, the length of the description, but still we are losing information. And by coarse-graining too much, so we are getting in a scenario where we do not have any more information from the original structure. And that could be, of course, a limitation for preserving causal relations among data. But also in the general setting of learning conditional probabilities in a latent space, it is not trivial to understand what is the conditional dependence that the architectures learn, and that will be a problem to address what is the conditional dependence among the latent factors. But still, there are some implications for going into this research field, and the first one has been for semi-supervised learning, and it has been provided an explanation for why you should learn. So typically, when we consider a classification task that is from the input domain to the classification domain, we are assuming a causal model that has the sensorial data as the cause and the effect of the labeling. So that we are trying to learn this kind of this causal distribution. But so in the in the semi-supervised learning, we are facing the case where we have only few labeled data, and we want to integrate with more information on the input data. And so if we have such causal relation between the sensorial data and the labeling, it has been shown that in the causal setting, there is no information between these two distributions. So any semi-supervised learning procedure will not be effective. But instead, it is more plausible that we are trying to solve the anti-causal problem. And so that it's the labeling that causes a given C input. And that way, integrating more information on the input data results in an improvement for the prediction. So while in the causal relation there is independence, the anti-causal one, this no longer holds. Also, there are implications for robustness and strong generalization, such that by learning what are different causal mechanisms, in first place, we have the independence, so that we are learning different representation of the world, but also we are learning what are shifts out of distribution, such that when we apply interventions, and this could play a role for strategic behavior. Also, there are many other implications for causal discovery, for enforcement learning, for continual learning, and in a broader sense for scientific applications. So at this point, we should also ask ourselves whether this is useful, or we could take just a data set with all interventions and try to create a very big neural network and try to generalize among those seen data points. So that could be a way, but it's important to note that causality is not an option. On machine learning is just an important complement. So with causality, we are learning also structures of data. And these are structures of words, so we are learning causal mechanisms that can be useful also in other scenarios. But also, the generalization properties are tied to models assumption. And this is true in a deep learning setting where our inductive bias influences what are the regularizations, what are the outcomes of the network. But that's not a very sharp now. While in the causal scenario, by taking assumptions, this becomes more explicit and that can be verified. So there are very interesting references for causal representation learning, and so also the main article is the best reference, but other studies have been important in developing this direction. And thank you very much for listening to me. I hope we can stay in contact. So here there is a questionnaire for the quality of the video, of the audio, and also to ask you what you think about this initiative. So you can find also more information this link. This is our lab at this department at the University of Trento. And yeah, that's it.